So today is the second class of NMR. And so last time we did Blackboard, basically explaining all the key principles. And I'm just going to remind you very briefly of some of the key concepts again. And we're going to do that using some animations. Because last week I told you about this rotating frame of reference, which sometimes is a little bit difficult to understand if you don't see things rotating. So let's look at that. So we're going to look at these animations. And I stole this from YouTube. Okay. So basically the lab frame of reference is here, and this is the rotating frame. And this is the radio frequency generator, right? So this is going to create the radio frequency pulse that you will see here. And you will see that the spin, which is aligned along the main magnetic field, B0, will here in the lab frame will start processing, right? And so the RF field has this component in plane, which is called B1, which is oscillating. So let's first look here. So we see that this peak is processing, and it's also going first along Z and then kind of going all over the place. So it's much easier to understand if you look at this peak. So if we turn on the RF field, we're going to apply this in-plane magnetic, oscillating magnetic field B1, which is going to tilt the spin, right? So we start along the Z-axis, and when we give a certain time of this pulse, we turn the spin in the rotating frame, for example, by 90 degrees, and then we turn the radio frequency off. So this is a 90-degree pulse because the spin flipped from the Z-axis to, let's say, the Y-axis in the rotating frame. And that produces a signal. So if we would now turn on the detector, we would see a signal. And in this case, at first, we're assuming that this signal doesn't decay. But of course, in reality, this signal will decay. So here, there's no decay. You just get this sinusoidal signal because the spin is rotating around. Okay. So looking closer, this is now the top view. This is the drawings like I made before. So you can see that in the lab frame, it's incredibly difficult to follow and to draw anything. But in the rotating frame, we see that the 90-degree pulse gives this spin flip, and then the spin will decay again, right? And that goes through these two mechanisms, T1 relaxation, T2 relaxation, which we'll also go back into. Okay, so the first one, T1 relaxation. This is from an MRI movie, actually, but basically so here you will get dizzy, but in the rotating frame, we give this 90-degree pulse. So the spin flips in the XY plane, right? Here you go. And then it starts relaxing. So it turns, the angle is decreasing. So theta is going smaller, and it ends up with all the arrows pointing in the Z direction. That's T1 relaxation. T2 relaxation is because local magnetic fields are influencing each other. So you see that let's say the total spin is not decreasing, but they're becoming randomized. So if you take the sum of all these spins, that actually decreases, right? So real T2 relaxation is because of this dephasing, as it's called. So the spins are getting dephased, and that reduces the overall signal that you are measuring. Okay, so that's the real T2 relaxation. Then we talked about also T2 star, which is not real, but it's because of inhomogeneous local magnetic fields. So your NMR is not very well shimmed, and there's some slower, some faster precession, some slower precession. So the spins, they are again dephasing, but because of local inhomogeneities in your magnetic field. Okay, let's look one more time. Right, so they start all in phase in the XY plane, and because of small differences, they are locally dephasing. Okay. So this is just, and that's why we don't typically use the lab frame, because you go completely crazy if you look at this too long. Okay, that was just to remind you of the key principles. What does the machine that you use actually look like? So nowadays, these magnets are very well protected. So they have different layers, and there's a good reason. So here inside, you have the magnet, right? Which is actually, it's quite interesting. So the coil of the magnet is wound by hand. So there are many, many thousands of turns you have to make on an electromagnet. It's done by hand, and there's only, I think, 2 factories in the world that can actually do it. But okay, so you have this electromagnet here, and it needs to be, it's a superconducting magnet. So to get superconductivity, you need to be very, very, very cold. And how do you get very, very cold? You use liquid helium, right? Which is not only very cold, but also very expensive. So so typically, for example, I don't know what the liquid helium price is nowadays, but typically to cool down the magnet from room temperature to liquid helium temperatures, you spend 5,000 or 10,000 euros, bless you, in liquid helium. Okay, so to lower this cost a little bit, they have different shells, and in a more outer shell, they will put liquid nitrogen, which is cheaper. So you use liquid nitrogen to keep cool the liquid helium, which cools the magnet. On top of that, there's also so there's these different layers. So they do just like in a thermos can that you use for coffee. There's a little vacuum layer in between for insulation. Okay, so then here you have your magnet in liquid helium, liquid nitrogen around, everything is nice. You also have magnetic shielding, right? So if you have a huge magnet, it's dangerous, because if people have a pacemaker and you pass by, then you drop that. So that's not good. So modern NMRs, they actually have a special new metal that shields the magnetic field. So it's actually quite safe to be around, even though in most NMR rooms, there will be a little line on the floor beyond which you cannot take any metal. So if you come with a metal scissors or something, it will fly to the magnet. That's not good. Okay, so that's the machine. And then inside this magnet, you will put what's called the NMR probe. So that's where the radio frequency field is generated, and also where the signal is detected. Okay, and these things on top, they are just to fill the liquid helium and the liquid nitrogen. Okay, so that's the equipment. Then this is the NMR probe. So that's what you put from the bottom inside the NMR machine. And if you look in the head of the probe, you cut this open, you will see a bunch of electronics. And here you see the radio frequency coils. Okay. And so your sample goes in what's called an NMR tube. It's just a glass tube that's like 15 centimeters long. And you put maybe 3-4 centimeters of liquid inside. So this will typically be a deuterated solvent like deuterated chloroform or deuterated water or anything like that. And you put that sample tube into what's called a spinner. So in many NMR machines, especially the older ones, the sample will turn around, because it will make the, let's say, it will make the sample more homogeneous and the magnetization more homogeneous. Nowadays, actually, the modern NMRs, they don't spin anymore, but this thing is still called a spinner. And why do you need to put this in a spinner? You'll understand that, because you have to, the probe is at the bottom, so the sample has to go in from the top, and that tube is like 2 meters long. So you need to drop your sample in from the top and let it fall down in a controlled way, right? So if you forget to turn on this airflow, so you blow air and the spinner will fly, that's actually fun. So the spinner will fly on this airflow. Then you turn the air off and the spinner will slowly go down along this tube. And so the spinner will descend, plop, and it will go into the probe, right here. Funny anecdote, I don't know if I should tell this or not. Anyway, but I used to be the NMR responsible of our group during my PhD. And so what people do in the lab to dry their tubes, these tubes, you reuse them, right? It's not one time and then you throw them out. So NMR tubes are reused. And so people rinse them with acetone and then you need to dry them. Okay, so what do people do? They put it in an oven, right? You put a beaker, you put the NMR tube, and then slowly over time, the tube bends tiny little bit. Okay, so it's a slightly bent NMR tube, you put it in the spinner descends, and then it doesn't fit into the sample probe here, and then crack, it breaks. Yeah, and then it breaks, your tube breaks here inside this thing, and then you have a huge mess. Okay, let's continue with the serious side. So similar kind of chart as we've seen for infrared is we have the chemical shift actually means something, right? So I will go in more detail on some of these groups, but you can just look at the chemical shift of your peaks, and that will tell you something about what kind of protons you have. So for example, there are very characteristic ones. For example, aldehydes or carboxylic acids, they will be very what's called downfield. Remember, downfield is high ppms. It's on the left side of your spectrum. And upfield is low ppms, this region. Right, so for example, allylic protons are more around 1 or 2 ppm, and aromatic ones are in this region. So again, you can just try to identify already by the range of ppms what kind of protons you have. Then, in addition, we also talked about this, is this spin-spin splitting, right? Which depends on the number of neighbors. So the carbon next to it, how many hydrogens are on that carbon? If there are no neighbors, then you get a singlet. Now, if there's one neighbor, you get a doublet. 2 neighbors, triplet, and so on, quartet. This one goes all the way to non-net. Okay, but like I said, often when it's not 100% clear what kind of coupling there is, they will just call it multiplet. But you should always try to really identify what kind of spin-spin coupling you have. Yes, question.
On the graph, there was the TMS.
Oh, right, TMS, that's the reference compound. So that's tetramethylsilane. That is by definition set to 0. And so often, okay, I didn't include that in the slides, but so often your solvent, so if you buy deuterated chloroform, it has a small percentage of TMS usually. If you don't want the TMS to be in your solvent, you can use a smaller tube, which is called an insert, which you slide inside the NMR tube with a little bit of TMS. So that is also sometimes done. Yeah, so TMS, as I said in the last class, is set to 0. And we're measuring the difference in the shift between TMS and whatever compound, right? Because I said last time that absolute frequencies are very difficult to measure in NMR. So we're always including TMS, and then in the software, you set TMS to 0, and then all the rest will work out. Okay, so these are, we're not going to go through each of those, but so there are tables like this one where for specific functional groups, you have specific chemical shifts, right? And there are some ones, we will go into some level of detail in this class, where it says var. This means variable, right? And so the chemical shift of these things can move. Usually the reason is that they hydrogen bond. So if you get some degree of hydrogen bonding, just like in infrared, you get a shift of your peak. So same in infrared, same in NMR. Okay, we're not going to go through this, but we're going to look at some trends. Okay, so if we look at a methyl group and we attach different elements here, right? So look at this series. This is TMS, right? Tetramethyl silane, which is chemical shift is set to 0. And you can see that there is a shift in ppms, which is called downfield shift, because it shifts to higher ppms. The more electronegative is your element. So fluorine is very electronegative, so the chemical shift will go downfield. Right? Oxygen is less electronegative, so it will be less shifted. Chlorine, even less shifted. Bromine, even less shifted. Okay, so the trend is more electronegative, more downfield shifted. Then also the number of these electronegative groups you attach. For example, if I have 1 chlorine, right, then I have chemical shift 3 of these hydrogens. But if I add 2 chlorines, it already goes to 5. And if I add 3 chlorines, so this is chloroform, then you're at 7 ppm. Right? So these effects are additive. If you add several electronegative atoms to a carbon that has a hydrogen, then it will shift more. And also the distance at which this electronegative group is positioned will matter. So if you're, for example, you have a bromine and you're just right next to the bromine, there will be a big downfield shift. If you're 1 position away, it will be less. And if you're 2 positions away, it will be even less. Right? So these electronegative effects, they are felt through different bonds, through different carbon bonds. Okay, so let's repeat again a little bit this splitting patterns, right? So if we look here, we have 2 columns. We have the upfield and the downfield shift. So chlorine will be more electronegative than bromine. So this one will be more downfield than this one, right? They are both doublets because I have 1 proton here, I have 1 proton here, so they both have 1 neighbor. So both are doublets. Okay, let's look here. We have 2 chlorines directly attached. So this will be the downfield region. I have 1 proton with 2 neighbors, so I get a triplet. Here I get these 2 protons. They have 1 neighbor, so I get a doublet. You're following, right? Okay. Let's look at these ones. So this looks kind of symmetrical, but chlorine is more electronegative than bromine. So this one will be more downfield, this one will be more upfield, and they're both triplets because they both have 2 neighbors. Okay, here I have this one, 2 chlorines directly attached. So downfield, it has 3 neighbors. So I have a quartet. Here, this one is farther away, so more upfield. And this one has 1 neighbor, so doublet. Here again, okay, so we have 2 closer to the chlorine. Downfield has 3 neighbors, so we have a quartet. This one has 2 neighbors, so we have a triplet. Here we have the bromine directly attached, so it's downfield. We have 6 neighbors, so we have a septet. And here these give an integral of 6, right? More upfield because it's farther away from the bromine, and 1 neighbor, so doublet. There you go, we did it. Okay, then I also said this last week. You can look, so when you have splitting, it depends on what type of splitting you have, what the distance between the 2 peaks is. Right, so the most common is this 3J, which I set all the way at the end of the course at 6 p.m. So you were probably all very tired. So it really depends. So 3J means coupling through 3 bonds, right? So I have from this hydrogen to this hydrogen, I have 3 bonds. 1, 2, 3. Okay, so you have to count the number of bonds. Here I have the same 1, 2, 3. 1, 2, 3. 1, well, this actually, yeah, 2, 3. The hydrogen is sticking out here. And So depending on the type of bond you have and on the configuration, you can get different couplings. This one is also always interesting. So cis coupling has a smaller coupling constant than trans coupling. Okay, so that's something to keep in mind. Then I told you also in the last class that there are NMRs and they have different magnetic field strengths. And usually the older NMRs, they have lower megahertz. So like I said last time, the megahertz is the precession frequency of protons at that magnetic field. So 60 megahertz means 1.41 Tesla, the electromagnet. So the protons will precess at 60 megahertz, and this is the same compound taken on two different NMR machines. So what do you see? Well, the first thing is that the center of these peaks is at the same chemical shift. That's why chemical shift is important. Remember, it's a difference in frequency versus TMS divided by the frequency of the machine. So you see that everything looks compressed on the 300 megahertz NMR, which actually is good. I think I have a zoom, right? So if we zoom in on those things, so you will often see, and in this class you will see it a lot, an NMR spectrum and then magnifications, so you can actually see what the shape is of these peaks. So if you compare these things, they don't look so different, right? It looks the same. So what's the point of having a 300 megahertz? If 60 megahertz, you don't need a superconducting magnet. You can just have a tabletop NMR. Well, if you get larger molecules, there will be many protons with different chemical shifts, and those things will start overlapping. So you'll have like a sextet overlapping with a triplet overlapping with a doublet, and then it becomes a mess. So let's say a stronger NMR with a higher magnetic field, higher precession frequency, will give you more resolution. So it's easier to resolve each signal, and then you can zoom in the software to look actually what the shape is of each of these things. So in this class, I will mostly show you 60 megahertz spectra, not because they're old, but because it's easier to resolve them. Okay, so we should have done this as a little exercise, but there we go. So let's look at these signals. So the first thing we can see, we have the nitro group, which is more electronegative, right? So this one will be more downfield than this one, and it will be more downfield than this one, right? So you see that the red peak is to the highest ppms, most to the left side, then the green ones, and then the blue ones. And if we look here, we have two neighbors, right? So we get a triplet. The one in the middle has 5 neighbors, so we get a sextet. And this one has 2 neighbors, so we get a triplet. Okay, it's clear? Yes. Okay, so now we can go through some different classes of compounds and some interesting parts of that, right? So this we already, we just saw in the coupling behavior. So cis and trans coupling of alkenes is different, right? Sometimes it will be difficult to see them, but if you see 6 or 18, you can kind of distinguish them from each other. There's also can be a small coupling between the 2 protons that are on the same side, because sometimes the rotation is not free. And if you have a molecule that cannot rotate, actually the protons see 2 slightly different chemical environments, and they can actually also cause splitting. Okay, so let's look at this molecule. So we have a double bond here, we have a methyl group, and then we just have an alkene chain over here. Okay, so what can we see? This one is most downfield. Okay, and then the farther you go away, the more upfield they shift. So the methyl group doesn't really feel this one here, so it will be around 1 ppm. Okay, let's look at, for example, B. B has 3 here, 2 here, so it has 5 neighbors, so this is a sextet. This one has no neighbors, right, because it's attached to a carbon that doesn't have a hydrogen itself. So we get a singlet. Okay, D here has 2 neighbors, so it makes a triplet. Okay, and you see that this is the splitting of these different protons. Okay, aromatics. So if you have any type of benzene rings, they're usually very downfield shifted, typically around 7 ppm. And even so benzylic protons, so next to the aromatic ring, they are not so much downfield, but they are slightly downfield from a normal alkane group. And you can have coupling behavior that depends on if you have ortho, so that means next to the carbon, sorry, the position just next to it, or meta or para, right? So this, and there's many, as you can see in this book, there's an entire chapter on all these aromatics and their splitting. So there's many rules and many well-documented cases in spin-spin splitting that you can consult. Okay, let's look at an example. So we have an aromatic group here. We have a chlorine here, which will be electron withdrawing, and a methyl group here. So what do you guys think? Let's first look at the integrals, right? So the integral is this number that is under the peak. So already from the integrals, it will be easy. Yeah, so the most upfield, and the integral is 3. Yep, go. Well, one thing you can see is that, so the aromatic region is always downfield. So likely these will be the aromatics. And here I have a CH2 on a chlorine, which is kind of downfield from alkanes, but not as much as aromatics. And this one shows a singlet. So it doesn't have any neighbors. You can see here, there's no hydrogen directly here. And here we have a chlorine. So this one will give a singlet with integral 2, right? So there's 2 hydrogens here. This one will give a singlet with 3, and these ones give, okay, it's difficult to see, but it's 2 and 2 basically. So here, these are chemically equivalent, right? And this, so this probably, okay, now we'll see if I'm right. This one will be slightly more downfield because of this induction of the chlorine. They are chemically equivalent, but they have 1 neighbor, so it will be a doublet. Yeah, it was right. Okay, so you can see this one, so it's a doublet because of this 1 neighbor. It's slightly more downfield shifted because of this chlorine here, but not too far from C that are also aromatics. Okay, so alkynes, so they are with the triple bond, they can have something funny. So first of all, they have a slightly downfield shifted chemical shift from normal alkanes, but they actually have a splitting that goes over 4 bonds, right? So here you see 4J, so that means splitting over 4 bonds. So if we count between those protons, right, we have 1, 2, 3, 4 bonds. But the splitting constant is very small. Okay? When they say splitting is small, they mean not many hertz. They don't mean the peak intensity. Okay, so now we're going to look at this graph, which starts becoming a little bit more difficult. So what do you guys see? What is this? It's a triplet, right? It has integral 3. Okay, yeah, it's this methyl group. This is the only CH3, right? So this one we can easily assign. Let's look at this one. It has integral 2, so it's a CH2, can be either one of these ones, but it's a sextet. So it must be this one because you have 3 neighbors here, 5 neighbors here. So this one will be sextet with integral 2. Okay, we also are going closer to the alkyne, so we're shifting more downfield. So here, this one, yes. So this one is integral 1, so it's this one, right? Is the alkyne hydrogen. But then what is this weird thing here? Is this a sextet or what is it? Yes, exactly. So how do you see that it's a triplet that is split? Well, you can answer.
There is a kind of symmetry of the. I don't know.
Yeah, there's a symmetry, but if you look at the peaks, they don't follow this Pascal's triangle. Remember? Yeah. So a sextet should be 1, 5, 10, 10, 5, 1. If you look at this thing here, it's not that, right? It looks more like a triplet. These two are together, these two are together, these are two are together. So that thing comes from here. So it has 2 neighbors on this side. So it makes a triplet. But it has allylic coupling here over 4 bonds with C, which makes a doublet. So it's a triplet of doublets. Okay, let's zoom in on those things. So if we look at this peak, so it's not a sextet, it has a 3J coupling, right? So the normal nearest neighbor coupling. So we're looking at proton D, right? So these 2 protons. So they look at the neighbors, which are 2 neighbors. So it gives a triplet. And if we look at so now we're going to look at the split, at the coupling constant, right? So if we look between 1, 3, and 5, that's one triplet, we see that it's 7 Hertz, which is the normal 3J coupling. And if we look between 1 and 2, 3 and 4, and 5 and 6, we see that it's about 3 Hertz. So that indicates 4J coupling, which is from the alkyne. Right, so we have the triplet, we have the doublet, so we have a triplet of doublets. Sorry, it's confusing. And this can happen in the same way with other things. So looking really closely at the shape of your multiplet. So don't call this a multiplet, but this would be a triplet of doublets. Okay. So why is NMR so cool and so powerful is because there are actually very good simulators. Remember in infrared that we said, it's complicated, we don't really know, NMR not, right? So NMR, this is, so if you have ChemDraw, which is the same program you use to draw your chemical structures, you can just draw your molecule. So this is the same molecule. And it will give you a prediction, and it will tell you actually how good the prediction is. So blue values means good prediction of the ppms. So it does not only predict ppms, but also the splitting pattern. So you can see that these things are lighting up, right? So you can just hover over the peaks, and it will tell you which proton it is. And it's actually really accurate, right? So if you have a basic molecule, you draw it in ChemDraw, click one button, it will show you the predicted spectrum, and then you compare it with your experiment, and it's pretty good. So that's the really big difference between, infrared, UV vis. You know, UV vis is nice, fluorescence is nice, but you're never going to solve a structure of a compound from UV vis or fluorescence. You just won't, right? And same for infrared, it's very difficult. But NMR is very powerful for that reason. Okay, let's continue a little bit. So alcohols. Alcohols are a bit funny, okay? So typically they don't give coupling. So if you have an alcohol next to a CH, no coupling. And secondly, the peak can actually shift again. So depending on if your molecule, your alcohol can hydrogen bond, or it's in a solvent that is more acidic or more basic, the peak will actually shift quite a bit, right? That's one thing. Because there's no coupling, usually it gives a singlet. It can couple in select cases, but usually not. And there's another weird thing. So alcohols, they have hydrogens that are slightly acidic, right? So they can actually be removed and they can be replaced. So if you have, for example, you have this molecule here, and you have the alcohol group here, which gives you a big singlet here. So this is in deuterated chloroform, right? So I measure my spectrum and I see this peak here. Now, if I, for example, change the temperature, this peak will shift in ppms. All the other peaks just stay the same chemical shift. But alcohols can shift. And if you add some deuterated water, this hydrogen can actually exchange, right? So the hydrogen is replaced by deuterium. And deuterium, you don't see it in proton NMR, right? That's why you use deuterated solvents. So this is called deuterium exchange. And you can actually use that to assign your OH, right? So if you have an alcohol, you measure it in chloroform, you just take your tube out of the NMR machine, you put 1 drop of D2O and the peak will disappear. And then you say, well, must be an exchangeable proton like an alcohol. So that's actually quite interesting for alcohols. Okay, ethers. Okay, so first of all, the protons that are close to the ether, so the ether is here, sorry. So there's a methyl group, oxygen, and then CH2. They are shifted downfield, right? I mean, the scale is every time different, so you have to pay a bit of attention. But it's downfield shifted versus the normal aliphatic protons because oxygen is electronegative. Okay. And then you see D is a singlet. This is a bit crowded here. So D is a singlet and E is a triplet because it has 2 neighbors, right? So this is not a multiplet, but this is a triplet next to a singlet. Okay, amines, they have again a characteristic shift and they can have coupling, but it's huge. And often you don't observe it, right? So 2J, so 2 bond coupling, you typically don't see it. And 3 bond coupling, you typically don't see it because of chemical exchange. Okay, so let's look here. So amines can do the same thing as the alcohols. So this proton is quite labile, so it can exchange with D2O to give you the deuterated version of that, which then has no signal. And I typically don't have coupling, so I will see a broad, so typically it's a singlet. It's somewhere in your spectrum, you don't really know where. And it's very broad if you compare, a single peak of these versus this super broad thing here. That's quite a difference. Okay, so let's look again at all the protons. So this one will be most upfield. It's CH3. It has 2 neighbors, gives you a triplet with integral 3. This one has 5 neighbors, so it's a sextet. It has integral 2 because there are 2 protons. Okay, you can already see that, so this integral is also 2. Often it's difficult to integrate because it's so broad and then the value will not be very accurate, but okay. And then this one has 2 neighbors, so it's a triplet with integral 2. Okay, nitriles, they are slightly de-shielded, not so much. So here we see this one, this is electronegative, so this one is the most downfield. It has 2 neighbors, so it gives you a triplet. These ones all have, so this one has 4 neighbors, so that will be pentet or something, yeah. And here the same, and again, the methyl group is the most upfield shifted, and it's a triplet. Okay, couple more to go. Aldehydes, they can also have an interesting coupling, and they are very, very, very downfield shifted, between 9 and 10 ppm. And the one, so the alpha carbon next to the aldehyde is slightly downfield at 2 ppm. Okay, there we go. So we look at this molecule. Again, so here we have 1 hydrogen, which is very, very downfield. So we see that the integral is 1, so that's nice. But we see actually that it looks like a doublet. And that's because this molecule has this additional splitting, which is very, very small, which gives you this, this doublet. Whereas you would normally think, okay, this is probably a singlet. But in this case, for aldehydes, it gives you a doublet, or sometimes they're just blended together. Sometimes you don't see the coupling. And okay, let's look at the most difficult one. So here we have a septet, but again with splitting. So if you look at Pascal's triangle, okay, I'm not going to draw it further, but you would expect this, this in distribution in intensities. But then because we also have the splitting from the aldehyde, this septet splits into doublets. So you have a septet of doublets. If we look at the splitting between the larger peaks, let's say, then you see that it's 3J coupling, 7 Hertz. And if we look at the smaller coupling, it's 1.5 Hertz. So it's very, very narrow. So here, if you would measure this on a 60 megahertz, you would not be able to resolve that this is a septet of doublets. You would just see 1 septet because the line broadness is too big on a 60 megahertz. So this is probably on a 400 or 500 megahertz NMR. And this one is a normal doublet, right, with integral 6, because you have 1 neighbor. So we get a doublet with normal 3J coupling, so 7 Hertz. We're almost there with all these weird examples. So carboxylic acids, they are very, very downfield, right? And they typically give very, very broad signals. So normally you don't like carboxylic acids in your NMR because they will kind of screw up your baseline. And the ones alpha of the carboxylic acid, they are slightly de-shielded. Okay, so let's look here. So actually, look at the scale here. So this one is like at 12.5 ppm, which is very far. A lot of people don't even record their NMR to 12, but maybe only to 10. So when you have a carboxylic acid, you should think, oh, maybe I should record a wider range of ppms. So that thing is here, and it can do the same as the alcohols, as the amines. Of course, this is known, it's an acid, so it has a labile proton. If you have some deuterium D2O present, it will exchange. So you get deuterium exchange. which then will kill your signal. So you can again, do your NMR in chloroform. The problem is that carboxylic acid in chloroform, they hydrogen bond. Okay, so the two carboxylic acids, they can flip around and they can hydrogen bond with each other, which then will be terrible for your solubility. So a lot of times people will, for example, add a little bit of metallic sodium, or they will change the pH to deprotonate the carboxylic acid, which makes it more soluble, which then allows you to get a nice NMR spectrum. Okay, so the alcohols are here. Here, this one is the most downfield shifted, right? Because of this electronegativity of the carboxylic acids here. This one has two neighbors, so it gives a triplet integral 1. And this one has 4 neighbors, so it will give you 5 peaks here with integral 2. And lastly, the methyl, again, most upfield triplet with integral 3. Okay, amides, very important in, for example, peptides or in proteins. Let's look at those. So here you actually get an interesting effect. So the 2 protons that are here, they are actually in this molecule a bit restricted from, so they cannot rotate as free as you would expect. Probably because here you can hydrogen bond with the carbonyl here. So that gives you 2 separate singlets. So you see that, so together these are 2 protons, but it's not a doublet, it's 2 singlets that are just slightly different in chemical shift. Again, methyl here, CH2 farthest from the carboxylic acid. This one is most downfield shifted because of the electronegativity. Okay, so what can you do? And I'll try in the last class to go a little bit. So the last class is mass spectrometry, and then we'll also try to do some unknown compounds. So how do you approach a problem where you have an unknown compound? So usually when you're in your internship and you're going to make some compounds, you know your starting compound. So it's not, I mean, otherwise it would be like voodoo chemistry, right? So usually you know your starting compound, so you have kind of an idea of the possibilities you're going to get. But let's, for now, just assume I give you a flask of some unknown compounds. So what do? Well, you start using different spectroscopic techniques. Or not, this is not spectroscopy, but this is a very old technique that no one likes anymore, but it's very powerful. And it's called elemental analysis. Did you already have that in one of your courses? No. Disappointing. Okay, so elemental analysis, I didn't include it in this course because I thought you all knew it. But basically in elemental analysis, you take your compound and you burn it, which sounds kind of violent, and it is. So you burn your compound and then you measure the gases that come out. So you measure CO2 and NO2 and all these kind of things. And that actually gives you a certain ratio between these elements. And typically it's carbon, hydrogen, nitrogen, sometimes oxygen, and sometimes some special element like sulfur. Okay, so if you're going to do an internship in organic chemistry, then you will submit your samples here in the faculty. There's a service. You put your sample. They need like 5 or 10 milligrams. They burn it so you don't get it back, and then they will give you this elemental analysis composition question.
When you burn something, doesn't that usually get tar that remains?
No. So if you want to, yeah, you can burn it either in oxygen environment or in nitrogen environment. So in one case, yeah, you really burn it, and in the other case, you decompose it. I'm not an expert on elemental analysis, I have to say. But it's a very, very old technique, that, hundreds of years ago, well, maybe not hundreds, but, 100 years ago, you could already do elemental analysis, whereas NMR, you could not do. Okay, so you get this back from the service. So we get carbon, hydrogen, nitrogen, oxygen, and they will give you the mass percentage. So how do I go from mass percentage to some kind of structural formula? Any ideas? Okay, I'm just going to do some crude things. So I'm saying, okay, this is my mass percentage. I'm just going to assume we have 62 grams. Okay, there are some.
You make the mass that match the molar mass.
Yes, exactly. So you try to convert the mass percentage to a molar percentage, which is not that difficult, right? So if I just, for easiness, I just assume we have 62 grams of carbon, 4 grams of hydrogen, and 33 grams of oxygen, I can calculate how many moles that is, 5, 4, and 2. And then I will basically set 1 to 1. So let's say we call oxygen 1. So I divide this by 2.08, this by 2.08, it will be around 2, and this by 2.08, it will be 2.5. But of course, we cannot have 2.5 carbon atoms, right? So I will multiply this list. So I get integer. Integer means 1, 2, 3, 4, 5, but not any decimal numbers, right? I cannot have 2.5 carbons, like half a carbon, doesn't exist. So you need whole number of moles. So the most probable structures that I have would be C5H4O2. But it can also be double that. It can also be C10H8O4, maybe. Or, it can be, so, but let's just, for simplicity, we assume it's the smallest thing that you could do. So if you look at this formula, okay, there's already a cheat sheet here, but is this a saturated compound? No, it's not. Saturated, if you have an alkane, then you have always the number of hydrogens should be 2n plus 2, right? Clearly, this is, 2n plus 2 would be 12, and we have 4. So clearly, there's something not saturated. And you can calculate what's called the degree of unsaturation. And so the degree of unsaturation takes into account the number of nitrogens, the number of halogens, and the number of hydrogens, okay? So you take your formula and you say, okay, 2 times carbon plus 2 plus the number of nitrogens minus the number of halogens minus the number of hydrogens divide by 2 is some kind of number. And in this case, it's 4, right? If we do 2 times 5 plus 2 is 12, nothing, nothing. 12 minus 4 is 8. 8 divided by 2 is 4. Okay, so degree of unsaturation is 4, which means we have either 4 rings or 4 sigma bonds. 4 rings would be highly unlikely in a compound that only has 5 carbons. So I think we can safely exclude the possibility that we have 4 rings. So we probably have either 4 sigma bonds, or we have 1 ring and 3 sigma bonds, or something like that. But more, based on this formula, more than 1 ring, I don't think so. So we have 1 ring and that. So now you can dream in your head of all the chemical formulas that we can potentially make. I did this morning. I could come up with 6. I think there are more, but okay. So I drew all these 6 molecules in ChemDraw. And ChemDraw is very nice. It gives you the formula, which is all the same, right? And the exact mass, which we're going to come back to in the next class for mass spectrometry, is all the same. So that's not very helpful. And the elemental analysis, if you compare all these things, is also the same. So if I give you 6 jars with these 6 compounds, you do elemental analysis, it will be identical. If you do simple mass spectrometry, which we're going to talk about next week, this M/Z ratio, which is mass over charge ratio, is also identical. So not very useful question.
But with elemental analysis, you only get percentage, right? So you can also have the double amount of all of these elements and have bigger molecules. Still do the same percentage.
Yeah. So exactly. So there could be even larger molecules that we don't know, but for simple, because there are already 6. If you include the double, it will be total madness in terms of possible compounds that you can make. But they all have the same formula and they have the same mass. So okay, but we have identified 6 different compounds that we possibly can have based on the fact that we have probably only 1 ring and the number of unsaturated hydrogens. Okay, then you take your compound and you walk to the infrared machine. This is from the previous class on infrared. And you will look in this region. So we're going to basically forget the fingerprint region because it's too busy. There will be a million of peaks. But we will look in this region and see what we find. Okay, this is the infrared of our unknown compound. What do we see? We see something at 2800, which is quite sharp. And we see something at 1700, which is quite intense. Okay, so let's look at this table, 2800. So either we have a carboxylic acid or we have an aldehyde. And that actually could correspond because if we have a CH stretch or an OH stretch, we also need a carbonyl stretch here. So we have the carbonyls here, acids here, and aldehydes here. So that narrows it down, right? So based on the infrared, I can already say, okay, it's not a ketone. So I can already kill everything that's a ketone here will go out. Great. So I need an aldehyde or a carboxylic acid. Okay. Now I measure the NMR. So I have 3 compounds left. This is the NMR of my compound. Which compound do you think it is? What do you see that is very characteristic? I said it half an hour ago. Very loud, yes. Yes, we have a big singlet. Maybe it's a carboxylic acid, but the chemical shift of carboxylic acids would be higher typically, and this would be a very broad peak. It's not, it's very sharp. No, it's a very sharp singlet. And if we go back in the class, I gave you this list and I told you with aldehydes that aldehydes are between 9 and 10 and sharp. So this thing, 100% sure, is an aldehyde. Oh, sorry, this is another table. Okay, so aldehydes between 9 and 10. Okay, and sharp, which is not on this table, but aldehydes are sharp. Acids are usually big, broad things. And you could add a drop of D2O, which would kill your carboxylic acid because of deuterium exchange. So you would easily find out that this is an aldehyde. So great. We know it's an aldehyde, so we can discard this compound because it's not an aldehyde. So we have these protons here, which would be this signal at 9.66 ppm. Okay, now how do we continue? So between, there, this one is dead. Okay, now between those two, what do you expect? And the hint I'm going to give you is look at the splitting. So we have a triplet, and 2 double doublets. Let's call them doublets, we don't care. So which compound between this one and this one would produce a triplet?
The middle compound.
Yes, the middle compound. Because if I look at this proton, it has 2 neighbors. See, this one has 2 neighbors. And here you don't have ever a situation where you have 2 neighbors, right? This one only has 1 neighbor, so it's a doublet. This one has no neighbors, so this would be a singlet. But this one has 2 neighbors, which is nice. So there you go. You found out that it's this compound. And so the NMR was much more instructive than the mass spec, sorry, not the mass spec, the infrared spectrum. Okay, we're good. And again, our friend ChemDraw, you draw this compound, it will nicely give you the chemical shifts. So this is the simulated spectrum, which I think it always takes 300 or 400 megahertz. So I have to zoom in to see the splitting. And this is the experimental result. So if we compare 9.66, okay. So 9.66 is really, this is experimental. So it's really spot on. Oops, there you go. 9.66, this one predicted 9.68, but it's really, really close. So the prediction is very good. The splitting pattern is very well reproduced. So again, the built-in simulator or the databases that exist give you a very good correspondence. Question?
But there's a pretty large difference in the end between experimentally and because the one doublet, the last one is higher than 8, but experimentally it's lower than 8.
Yes. Yeah, it's not infallible, let's say, but the if you get this spectrum and you simulate this, you can definitely see the which one is more downfield and which one is more upfield. So it's not 100% perfect, it's true, but it's pretty decent, and it really allows you to solve your structure quite fast. And there are databases, which I have on my last slide. I have a list of databases where you can look up. People have measured a lot of spectra and they have all put them in databases. Sometimes they're a bit old. I think this spectrum was measured in 1999. It's a bit old, but okay. Okay, last little exercise. So we have 2 unknown compounds. They have this elemental analysis, but as an extra info, otherwise you'll never solve it fast, is they are esters of acetic acid. Okay, so let's look at acetic acid. So we already have 2 carbons here, right? So you have 3 carbons left to play with. We calculate the degree of unsaturation, and it's 1. So either we have 1 ring, or we have 1 sigma bond, but there's already a sigma bond here, so no ring. Okay, no ring, 1 sigma bond. Okay, because it's almost time. These are the NMR spectra. So we have the 2 different compounds, esters of acetic acid. What do you think the structure will be and why? Let me draw. Okay. So on this dashed line, we still have 3 carbons to give away. So there are really 2 options only. So What are the two options? I need 3 more carbons there. Either it's linear, or it's not linear, right? So it's, okay, so we have these two. Now, which spectrum belongs to which compound? It's pretty easy if you look at the splitting. Oh, my pointer died. Pointer. Okay. Pointer's giving up. It's too late. Okay, what do you guys think? Can we vote? Yes. Sorry, you really need to speak loud. What do we think? We all agree? Yes, we all agree. Yeah, so indeed. So here we have 1, 2, 3, 4, 5, 6, 7. We have a septet. So that's, of course, because we have here 6 neighbors. We have an integral, which is close to 1. Okay, these things are not that accurate, but 0.9 is basically 1. And that gives you that compound. There you go. It's resolved. Okay, any questions? Yes. Yeah, so if you're closer to something that is electronegative, you will be more downfield shifted. If you have more electronegative atoms, let's say you have 3 chlorines, it will be more downfield shifted than 1 chlorine. So it's additive. So you basically look at what's the local, you know, how many electronegative groups are there around. If there are many, it will be far to the downfield.
For some groups like synthetic acid or how do we understand what is the explanation of this shift?
It's also electronegativity. So that's like the main first thing you consider is like what electronegative groups and how many and how far are they from the carbon where your proton is located. So if you shift, let's go back here, right? So if you are, let's say, 1 chlorine, you will be at 3 ppm, but 2 chlorines, 5, 3 chlorines, 7. So this is more chlorine, so more electronegative groups. Then if you see, for example, fluorine or fluor is more electronegative than chlorine. So this will give you already 4 ppm. So imagine you put 3 fluors on 1 carbon and then you have a neighbor, then it will be super, super downfield shifted. Which, sorry. Okay, the last slide, sorry. Yeah. Oh, it was almost the last slide, but okay. Yes. So, okay, so these ones will give you 6. It says 5, but again, the integrals are not super accurate, and you should divide everything by 0.86. But this is 6 hydrogens. They are very far from this ester, right? So they will be more or less a little bit downfield from a normal methyl group. And they're a doublet because I have one neighbor. And then this one, it's closer to this carbonyl, so it's more downfield shifted. And it has no neighbors, so it gives you a singlet. And then this one, which is, let's say, right on the oxygen, which is quite electronegative, right? Which will be the most downfield shifted. Integral is 1, and it's a septet because of 6 neighbors. Yes, exactly. Yeah. There's more effects that I'm not covering in this course, but more or less, yes. Okay, sorry. Last thing to finish. So these actually, so ChemOffice, ChemDraw is very good at NMR prediction. This is a free website that is reasonable. Sometimes it doesn't get like allylic splitting correct, but okay. And then there's these databases where you can basically look by the chemical formula. Will give you infrared, mass, Raman, NMR. And this is quite nice. There are exercises. Let me just quickly go through this website. So you can actually, oops. So there are exercises that just give you the chemical formula, and then you have to solve yourself. Oops, you have to solve what the spectrum is, and then you have to draw it, and then it tells you right or wrong. So it's a good exercise if you want to do that. It's on the last slide, this bottom one. Okay, thank you, and see you next week.